Our senior project's main focus was to provide support in the transferring process of the company's manufacturing line into a new facility. Due to the company conducting its clinical trial phase currently, we were asked to not share the company information. Our advisor is Dr. Masihin, and our group consists of Z, Derek, Fook, and Hussein. Project agenda. We will first introduce the company, define our objective, and state the current situation. Then we will dive into the different improvements that we have made during the transferring process. Lastly, the team will finish up with company's future state, conclusion, and recommendation. This company is located in Irvine, California, established in 2008. They are a medical device company that solely focuses on the carotid baroreceptor endovascular catheter. This means that the device will go into the main blood vessel, travel up to the neck artery, release the stent, then the stent will help regulate blood pressure by signaling the neurological pathway. Our team's main objective was to assist the quality engineer manager to transfer the production line to reduce the total production cost. Within the duration of the project, the team was able to learn industrial standards within the medical device community theoretically and through hands-on experience. Next, Food will talk about current situation.
Current situation. I will cover product outline, how it made, final product, packaging, and labeling. Product outline. The endovascular catheter had two major assemblies. In Figure A showed the inner assembly made of 4 components. Figure B showed the outer assembly made of 10 components, and everything bonded together by Loctite 4307. How it made. These are the 4 sub-assembly, each assembly made of 2 components bonded together by Loctite 4307. Final product. This is the actual product that Z built during the training process. Final packaging. The final step of production required function check. Then the catheter gets sealed off inside a Tyvek pouch with the label, show the lot number, and the production date. Device assembly procedure improvement. Fixture design and implementation of UV box. Fixture design. One of the components has to be measured and cut at 27.5 plus minus 0.3 centimeter. The fixture that our group designed allowed us to cut 5 pieces at a time without measurement. This cut down the lead time by 80%. Now Z will take over.
The company decided to use UV box instead of the UV glasses with the consideration of safety issues for the surroundings. The team want to know if the change is a comprehensive solution by comparing the process time before and after the implementation of UV box. The team first performed the time study before and after using the UV box for 2 assembly processes, then run the normality test to see if the collected data falls into normal distribution. The test result for all collected data show that the p-value is greater than 0.05, so we fail to reject the null hypothesis and indicate that all data is normal distributed. Now we can run the pair t-test. The null hypothesis is the time spent before and after using the UV box has no differences, and the alternative hypothesis is the other way around. The results show that the p-value is greater than 0.05 for both processes. So we fail to reject null hypothesis and conclude that using the UV box does not slow the process down.
Next, I'm going to be talking about the tensile testing result improvement, and specifically I will be covering the bag sealing design of experiments. The reason bag sealing is so important in the medical device industry is because there's a high risk of contamination. There's around 850,000 device-related infections a year, and poor bag sealing contributes to that, so it's important to make sure there's a high quality seal. Bag seals need to be strong enough to endure shipping and transportation, but easy enough to open by a medical practitioner. To tackle this problem, we use design of experiment techniques, and what design of experiments is systematically manipulating the input variables to observe the output variables, and we use this to design our bag system. The input variables of our bag seal machine were temperature of the heating element and the time it pressed down on the top of the bag. And currently the company average is 2.6 pound-feet, with 2.0 to 3.0 being acceptable and 3.0 being optimum. So we aim to optimize that and get as close to 3.0 as possible. The first step in the process is assigning coded factor levels to our high and low temperature and time settings. So for the temperature we have 290 low, 300 high, and for time we have 2.5 low, 2.9 high, and the low would correspond to -1 and the highs would be +1. Here is our coded design matrix for the experiment we ran. So for the first run we'd have temperature high, time high, and this would be the interaction effect, and we did 5 replications. And for here, for example, on number 3, we have temperature low, time high, and here are 5 replications. Here we gathered the averages of the high level of each factor and the low level of each factor, and took the difference, divided it by 2, which would be delta over 2, and here we have the absolute value of delta over 2 in this row. Here we developed a Pareto chart to show which factors have the most effect on the seal strength, and we can see that the most contribution comes from the temperature and time interaction and temperature itself. Here we obtain our prediction equation, which predicts the tensile strength of the bag seals, and it is obtained by gathering the grand average of all the trials and adding the half effects and the corresponding factor levels. Next, we solve for the variables in our prediction equation, which would give us a bag seal strength of 3.0 right here. And we did this by setting the time factor to high and solving for the temperature factor, and the coded value for the temperature factor, which would give us a tensile strength of 3.0, was 1.24. Next, we converted our coded factor level setting of 1.24 to an actual value in Fahrenheit, and we got 301.2 degrees Fahrenheit. This would give us a seal strength of 3.0. And next I'm going to hand it off to Z to discuss the device components bonding.
From the tensile testing result of bonding made by new employees, we see that some data points are below the lower specification limit, so the team decided to conduct more training on them. The team also gathered the data of tensile testing results before and after the training, and performs normality tests, which all data falls into normal distribution. The team chose to use pair t-test because the size of data is small. The null hypothesis indicates that the result mean have no difference, and the alternative hypothesis indicates that after training has a better result than before. The test result shows that 2 out of 6 tests have significant improvement. Now we are going to talk about the warehouse redesign. The team has studied that all the equipments and inventories are able to be stored in the warehouse, so we will mainly focus on the operational process here. Now we can take a look at the initial layout for the warehouse. For example, for the route of retrieving is all the way from the left corner to the right corner, which shows that the travel distance is very long. However, only considering the travel distance for a single task for each travel is not enough. The team decided to study the travel frequency for each task and calculate the total travel distance that is required to complete one batch for the products. Combining the factors that could affect the design of warehouse, the team redesigned the layout as shown on the right side. From the previous example, the travel distance for retrieving is reduced to 38 feet. In general, this redesign does not reduce the travel distance for each single task because the company rents some space out to the other companies, which they also want some place closer to their task. But overall, the total travel distance has been reduced close to 50%. Now I'm handing to Derek.
Future direction. The company is exploring ways to shorten the production period. To limit operators' uncertainty during production, the production procedure the team revised still need to be improved due to the lack of assertive and detailed actions. Sanding procedure is also a challenge. The company is undergoing trial and errors to see if the sanding will make a significant difference on the tensile strength. Limiting bioburden is another priority that needs to be tackled. Conclusion. After improving procedure and test method, validating sterilization processes, and enforcing quality control, the team is now more capable, knowledgeable, and confident in executing production setup and process. We also exceeded the engineering manager's expectation by successfully completed 3 lots of production during projected timeline and replaced expiring products. Economic analysis. After the transfer of the facility, the company will save 14% after 1 year of production. As the chart on the right shows, after the third production batch, producing in-house will become less costly compared to the outsourcing price, and the saving increase exponentially. Recommendation. This first recommendation is if the sanding procedure is necessary after all. The company should look into creating a fixture to help compensate the bottleneck. Next, if the company wants to achieve the targeted back seal strength, a new material for the pouch would be necessary to avoid the chance of burning through the seal. Third recommendation would be when consolidating the facility layout to shorten the travel distance between the inspection area and the clean room. Lastly, as the company grows bigger and bigger, standardized inventory system would be recommended to keep all the raw materials as well as the finished product accountable. Last but not least, this project would not be possible without the help of every faculty and staff in the IME department. Special thanks to our advisor Dr. Masihin's assist and guidance. Also special thanks to our quality engineer manager Wu for giving us this opportunity before we step into the engineering world.